All right, second way to find pH is the pH of weak acids and bases. So these problems are pretty simple to recognize for a couple reasons. We know that in this particular problem, we're asked to find a K. Strong acids and bases don't have Ks, right? Because they 100% dissociate. Not going to have the need, well, it's not that they don't have Ks, but they're so huge we don't even deal with them. They're not recorded on normal tables and things like that. Another thing is, if we look at that acid, isn't that a weak acid? And yes, it is. Why is this considered to be a weak acid? Carbon-containing acid, benzoic acid. And so what we're going to do, and this is something I want you to jot down somewhere in your notes, the first step to any weak acid-base problem is to start a rice table. And in your rice table, you are always and forever going to take your weak acid or base and add it to water all the time. So we're going to take our weak acid, our HC7H5O2, and we're going to add it to water. Equilibrium. And now we do a Laurie-Bronsted acid-base reaction. These are super simple. Only one H is going to be transferred. Since the benzoic acid is an acid, that's going to be a proton, what? Donor. So what are our two products going to be? H3O plus and C7H5O2 minus. Okay? So whenever they give you a concentration of an acid or base, that is always the initial concentration in the solution right here. So this was given to us in this problem as 0.100. If we need to find the equilibrium constant, we need to find all the equilibrium line concentrations. I love doing this. Love getting rid of stuff. Why are we getting rid of that? Because it's a pure liquid. So when you first start your table, assuming no dissociation yet, minus, we have the zeros there. And then we're going to shift reaction to the right. We're going to lose X, and we're going to gain X, and we're going to gain X. What's really cool about acid-base is that it's always Laurie-Bronsted like this, so you're only transferring ever one H, so you're never going to have two X's or three X's, because it's always going to be a 1-to-1-to-1. That's good and makes life easy, but we tend to get lazy. And so when you get equilibrium problems again, people forget that you're actually, you actually are raising it to that coefficient in the balanced equation. So just always remember that we're kind of just on a little X vacation here. So we're going to add up the lines. We get 0.100 minus X, X, and X. Now, in order to solve for the K, we need to find X, right? So we can plug X in and solve for all those equilibriums. There's another piece of information they give us. pH, that's correct. How is that going to help us? Exactly. pH is going to give us our concentration of our H plus, aka H3O plus ion. So at the end of the day, that will give us X. All right? So how do we find it from pH? What do we do to get from pH to H plus concentration? 10 to the negative 2.59. So go ahead. I'm not going to round to sig figs till the end, so just give me a bunch of numbers here. All right, can I get a second on that for the video? All right. One thing I want you to pay attention to. What's different here is when they do the scoring on the AP, usually one of the multiple points that you earn is for identifying what the concentration of the H plus is. So just writing X equals this number is not going to earn you that point, because you can't just say, oh, it's X. And as a reader, I can't be, oh, it's X, so they know that that's the H plus concentration. We're going to be looking for it within the body somewhere. So make sure that you say H plus or H3O plus is equal to that value, because that's something we specifically look for. Okay? All right, now that we have X, we can go ahead and put it in. Some of you might be thinking about dropping X at this point. We don't drop X if we know it. There's no reason to drop X if it's given to us. The only time we drop X is when we're trying to solve, and it kind of alleviates, the need for the quadratic or something like that. There's no reason to not do that math right there. So this is 0.00257, 0.00257. So how do I solve for the K? What? Products of a reactants. Because now we're an acid base, and this is an acid, we're going to make our K a little more specific, and we're going to call it a Ka. And that's going to be equal to H3O plus and C7H5O2 minus products over, we leave out the liquid and just write HC7H5O2. Some of you still on the test, I got a word from Miss Rozier. She asked me, did you tell your kids to write the expressions? I was like, yeah, many times. Some of you still aren't writing that. And you're going to lose at least a point per problem for every problem you don't do that. Okay? So now we can plug our stuff in. What was our K? Oh, we're solving K, excuse me. So Ka equals 0.00257 squared, because it's 0.00257 times 0.00257, divided by 0.1 minus 0.00257. So let's look at sig figs before we end up doing it. So we have a 3 sig fig number for the concentration, and how many sig figs is that pH? 2. So what do we want for a final answer? 2. So to 2 sig figs, what's our K? And can I get a second? And that is our answer. Pretty easy? Any questions? All right, so we're going to do the next problem. Essentially the same thing, except instead of calculating a Ka, we're looking for what? What? Kb. Why do we say that? Ammonia. What is ammonia? Weak base. Mr. Literal, yes, you're right. What is ammonia? It is NH3. You are correct. It is a weak base. So because of that, because it's weak, we're going to do a Rice table, and we're going to add the weak acid or base to water, always and forever. So RiCe NH3 plus H2O. Since it's a base, it's a proton acceptor. So we get NH4 plus OH minus. Our original concentration of this is 0.1. So our setup is very similar to our last problem. We're going to lose X, we're going to gain X, and we're going to gain X. So our equilibrium line looks like it did in the last problem. So this time, though, the pH can't be used directly. What's our problem? Yeah, we need the concentration of OH. So what do I need to do to get that? Minus 14 to get POH. The transition from pH to POH, you don't have to show that work on the AP. You can just do it. And so what is the POH of this? 2.87. So to get the OH concentration, I'm going to do 10 to the negative 2.87. So what is the OH concentration, which is equal to the X? Again, I want you to label that as such. What do we get? Don't worry about sig figs yet. 0.00135 moles per liter, and that is our concentration of OH, which is also equal to X. So we're going to put that in here for all the X's. So now our expression is going to be a Kb expression this time, is equal to NH4 plus times OH minus divided by NH3. So when I solve, my Kb is equal to 0.00135 times 0.00135 divided by 0.1 minus 0.00135. All right, so what is Kb? How many stick figs are we going to do again? 2. What do we get? And that's actually what it is in real life, so this was good data. We're going to be using the Kb of ammonia and the Ka of acetic acid, which are the same number, so much. By the end of the year, you're going to know 1.8 E negative 5 like this. It's just going to come straight out really quick. Okay, last problem of the day, short day. Calculate the pH of a solution, which is 0.712 molar methylamine. So here's when I'm saying we need to find pH of all these different things. This is what I'm talking about. The first question you're going to ask yourself is to classify this. It's important for you to recognize, remember that this is a nitrogenous base, right? Okay. What would be another indicator that this is a base? Kb. Okay. They're going to be giving you hints, but the important thing is to classify the type. Because that looks easy right now, but when we get to hydrolysis tomorrow, some people start to get that common ion confused with this. So we got to make sure you stay on top of it. So we're going to start our rice table. And because it's a weak base problem, you always take your weak base or acid and add it to water. Methylamine plus water. Since it's a weak base, that is a proton acceptor, so it's CH3 what? You guys tell me. Writing the equation from here on out is going to be the battle. Like, once you get that done, you're never going to have problems. Plus OH minus. And it's this OH minus that's making it basic. So our original concentration is 0.712, 0 and 0. We're going to lose X, we're going to gain X, and we're going to gain X. 0.712 minus X and X and X. Now, because we're in the weak acid genre, and I know we did this with KSP and didn't talk much about it, we really do need to make sure by using something called the 5% rule that trumping this X, remember the Donald Trump rule? Trumping that X is mathematically legitimate. Like, can we really do that? And so once we're done with the whole problem, we're going to calculate something called percent dissociation. What do you think percent dissociation means? What percentage, what? Dissociated. What percentage of my original amount broke up? If less than 5% does that, then we were okay dropping X. Now in your homework, I saw there were a few problems that were like a little bit above 5% and the key doesn't go back and do it again. That's fine. Just be aware of it. Be aware that you really probably should be going back and putting the X back in and resolving. Okay? On the AP, because graphing calculators here would be an advantage, they are probably not going to give you, or I know they're not, they're going to always let X be droppable. I just need you to understand that it's not always droppable because you're going to be taking chemistry at some point in college. And not all professors are cool with you just dropping X. They want you to do it the other way. So I need you to understand that process. So with that being said, how are we going to solve? We got to get pH, right? So what are we trying to look for to get pH?
The molarity of the hydroxide.
Exactly. The molarity of the hydroxide here, which is X, right? We can then do the negative log of that to find what? POH, and then we can do 14 minus that to find pH. So that's kind of where we're going. So we have to solve for X. So we're going to do our Kb expression of OH minus times this ion, this acidic ion, divided by CH3NH2. So our K they gave us is 4.4 times 10 to the negative fourth equals to X squared over 0.712. So this is where it's even more important to say that X is the OH concentration, because you're going to do something with that. Your X, which is your OH concentration, is what? Say that totally louder. I totally didn't hear that. 0.0176 what? 997. It's a lot of sig figs, which we'll take care of, but is that, can someone give me a second on that? All right, so that is equal to our mole per liter hydroxide ion concentration. How does that help me find pH? What do I do? Negative log of 0.017699 is equal to the pOH. So what is that value? Now we can look at sig figs. We have 3 in the molarity. There's a controversy. Don't use the K, use the K. They always end up making most of your stuff the same number of sig figs. I say let's just use the K, all right, because that is experimentally determined. So we're going to say 4.44, that's 2 sig figs. So we're going to round this pOH to 2 decimal places. What do we get? 1.75 is equal to the P. Are we done? Nope, we need pH. So when you start the problem, which I failed to mention, what kind of predict where the pH should end up? This is a base. Even though it's weak, it's a base. So you know you're expecting something above 7. Well, if you stop here without this being pH, thinking that this is pH, you can see, oh, that doesn't make sense. All right? So just be thoughtful when you're doing your problems. All right, what do we get then? 12.25. Did I hear someone say something? Question? Okay. So I chose to do a base problem because it has this extra step right here. When you're given a weak acid, it's easier because the X is actually equal to the H+, and then you just take the negative log of that, and that's just straight up pH. So that's why I chose to do this one. Let's go ahead and verify that our X was legitimately dropped. What was our percent dissociation? Percent dissociation is so easy to find. Don't be afraid of it. It's just the amount that broke up, the amount that left, over the original concentration times 100. How much left? X. So you take your X and you put it over the original concentration. That makes sense because that tells you how much dissociated times 100. So our X is 0.017699. I'm about to sneeze. Divided by thank you. 0.712. I covered the mic, so hopefully I didn't blow out anybody's eardrums. All right, what percent did we get? 2.5-ish%. We don't really care about that number all that much. We just know that, yeah, that's below 5%. So it was okay for us to drop the X. All right? All right, so work on your homework. You should be able to complete all of it. And if you're above 5% on any of them, don't freak out. But go ahead and calculate it.